In this video, you're going to learn how to create 7 carbon atoms in terms of forming bonds and their derivatives. And this here is going to be important when we are dealing with hydrocarbons in organic chemistry. Now, the first step that we're going to look at is the following. We're going to look at how to create long and branch chains related to 7 carbon atoms from one end to the other end, and this is going to lead us to the second step, which is how about creating cyclic compounds which will have either 7 carbon atoms around this system, or we can have something less but we can have branches around it. And this is going to be followed by carbonyl and carboxylic acid groups either separately or together, and this is going to be where we're going to dive into keto-acid compounds, where we're going to have a ketone and carboxylic acid group in a chain system or a cyclic system. So let's dive into the first step. Our first step looks at linear saturated hydrocarbons, where in this case where you have 7 atoms that are carbon and are joined together by covalent bond in a straight or linear system. This is considered to be called the N-heptane. Hep in this case means 7, and means in this case that it is on a linear continuous no branching system, and A and E represents a single bond. And this here is going to lead us to some branch versions of R and Hexane. And in this case we have our first one, which is going to be focusing on 3-methyl hexane, where on the third carbon that is around the longest continuous chain, which is in this case 6 carbon atoms, there is a methyl group that is attached to that third carbon. The next one is 2-methyl hexane, where on the second carbon on the longest continuous chain we have a methyl group that is attached to the 6th carbon chain. Then next now is 2,2-dimethyl pentane, and we have the longest continuous chain to be 5 carbon atoms, and on position 2 we have 2 methyl groups that are attached to that second carbon. And this is going to be followed by 3,3-dimethyl pentane, where on our 5 continuous carbon chain we have on our third position 2 methyl groups that are attached to that carbon. And finally here is 2,4-dimethyl pentane, where on our carbon 2 and carbon 4 on our longest continuous chain we have methyl groups that are attached right there. For our second part, we're going to be looking at diverse cyclic hydrocarbon, and we're going to start off with cycloheptane, where we have all carbons joined together and they form a cyclic compound, and there is no branching coming off this particular cyclic compound. So in conclusion, this here is called a cycloheptane. Next is cyclohexins, and we have 2 versions here. For example, we have the main hex to have a cyclic form, while we have a particular carbon atom above, and this is bonded to the carbon 1 and carbon 4 of our hex or cyclohexane, and therefore this is how you are going to be creating one version of a cyclohexane. Another version is where we have 1 carbon that is attached to carbon 1 and carbon 2 within the cyclohexane, and this is now going to be leading to how about we're dealing with 4 carbon atoms that are bonded together in a cyclic manner. This here derives the following, where we have not 1 but 2 but 3 methyl groups that are attached to carbon 1, 2 and 3 within that particular cyclobutane compound. And finally here is how about 5 carbon atoms that are bonded in a cyclic manner. This is called a cyclopentane. However, this is going to be having 2 methyl groups that are bonded to carbon 1, and therefore this forms a 7 carbon atoms that are bonded together. The third addition is, how about we have one of the carbons to be attached to oxygen in terms of looking at the derivatives of this. In this case, we're going to have 3 versions for now. One version is an aldehyde where you have the carbon attached with double bonded to the oxygen with an R group and then with a hydrogen, while the other version is looking at the ketone where the carbon is attached to 2 carbon or R groups at both ends with a double bond to the oxygen. And finally here we have carboxylic acid group where 1 carbon is attached to an R group, a hydroxyl group, and doubly bonded to an oxygen. Our goal here is to be able to look at how we can bring 2 of these functional groups together in a chain system or cyclic system. Like for example, we're going to combine carboxylic acids and ketone in a cyclic or chain system. So let's dive into that. First goal is to look at ketone carboxylic acid in terms of linear system, and for linear system we have 2 examples where the first example has a long continuous chain 7 carbon atoms, and on our first carbon is the carboxylic acid, while if you count from right to left on our 5th carbon we have the ketone present there. Therefore, since ketone is least priority in terms of naming, we are going to have it to be named oxo, therefore 5-oxo-heptonic acid. The next one example is where our ketone is not at the 5th position but rather the 4th position. This is going to be named 4-oxo-heptonic acid. This is going to lead us to the other part, which is where our branch keto-acids is going to be established, and we have 4 examples here to share with you. One example is 2,2-dimethyl 4-oxo-pentonic acid, and in this structure you see that at carbon 2 we have 2 methyl groups that are attached, and that is the least priority, and then the more priority group is the ketone group, which is positioned at carbon 4, and finally pentonic acid is the longest chain that is achieved for the carboxylic acid group, which is 5 carbon atoms. Keeping with the 5 carbon pentonic acid theme, we have the second version, which we have position of our oxo to be now at 2, while our dimethyl is at position 3. In this case, we are going to generate a 3,3-dimethyl 2-oxo-pentonic acid, followed by our next one where instead of our carbon 2 to have a methyl group, we have an ethyl group. And we have our position of our ketone to now be at position 4. Therefore, this is going to be named 2-ethyl 4-oxo-pentonic acid. And finally here, there is a wonderful distribution of our methyl group, one at position 2 and the other at position 4, while our oxo is now placed at position 3. Therefore, this is going to be named 2,4-dimethyl 3-oxo-pentonic acid. Finally, we have our cyclic ketoacids, and in this case we're going to assign our ketone within a ring, and this ring will come in 2 forms. One is the 4-membered ring, where on our first case scenario we have carbon 2 and carbon 4 within the 4-membered ring to have the methyl group present, while on carbon 3 within the 4-membered ring we have the carboxylic acid attached right here. However, this is not the case for the second version, where our cyclobutanone has a carbon 2 attached to the carboxylic acid, while our carbon 3 and 4 within the ring is attached to methyl groups. Now this leads us to the 5-membered ring version, where we have our cyclopentanone and our carbon 2 is attached to 2 groups. One is our methyl group and our carboxylic acid group, while other version here we have a shift in the position from position 2 to position 3 within the ring, but we have the same functional groups, which is the methyl group and the carboxylic acid, all attached to that carbon 3 within the ring. Overall, I hope you found this really informative in terms of creating awareness about the diverse ways by which you can represent your 7 carbon atoms in terms of not only forming long chains versus branch chains, but also awareness about cyclic compounds. Another one is to keep in mind is any derivatives in terms of 1 carbon attached to other functional groups that may be of interest to you, and also how multiple functional groups can actually be integrated in the same chain of focus. So I hope you found this very informative. Please hit the comment down below. Let me hear your thoughts. There are many more functional groups out there that you can play around with, but we didn't address that on this video. All the same, stay smart as always and believe in yourselves.